It only takes 30 seconds. 30 seconds for everything you've ever known, your city, your family, your entire world, to vanish into fire, wind, and radiation. No warnings, no time to run. One flash in the sky and it's over. This isn't a science fiction scenario. This is the very real and terrifying potential of nuclear weapons. And the truly frightening part, we've built thousands of them. To understand why nuclear weapons are so dangerous, we need to start with how they work. The heart of a nuclear bomb lies in a principle so small it's invisible, the atom. Inside every atom is a nucleus made up of protons and neutrons held together by the strongest force in nature, nuclear force. But if you break apart that nucleus, a chain reaction can be triggered. This process is called nuclear fission, and it's what powers the atomic bomb. A fission bomb uses either uranium-235 or plutonium-239, two materials that are fissile, meaning they can sustain a chain reaction. When a neutron strikes one of these atoms, it splits, releasing more neutrons and a massive amount of energy. Those neutrons then hit more atoms, creating a rapid, unstoppable chain reaction. The trick is getting a critical mass of these atoms together fast enough and tightly enough that the reaction doesn't fizzle out. That's where bomb design comes in. There are two main designs, gun type and implosion type. The gun type is simpler. It works like a cannon. One piece of uranium is fired into another to form a supercritical mass. When they combine, the chain reaction begins, releasing energy equivalent to thousands of tons of TNT. This was the design used in the bomb dropped on Hiroshima. The implosion type is more complex but much more powerful. It surrounds a sphere of plutonium with precisely shaped conventional explosives. When detonated, those explosives compress the plutonium core inward in perfect symmetry. That compression increases the density of the core and forces it into a supercritical state in microseconds. The chain reaction begins and the result is catastrophic. This was the design used on Nagasaki, and it's the foundation of most modern nuclear weapons. But even these are considered the small nukes. In the 1950s, scientists developed a second generation of nuclear weapons, thermonuclear bombs, also known as hydrogen bombs. These are not just more powerful, they're orders of magnitude more destructive. A hydrogen bomb uses the energy from a fission bomb to ignite nuclear fusion, the same process that powers the sun. In fusion, light atoms, typically isotopes of hydrogen, combine to form helium, releasing even more energy than fission. But fusion requires enormous heat and pressure, which only a fission bomb can provide. So a hydrogen bomb has two stages. The fission bomb triggers the fusion reaction. The result? A weapon that can unleash tens of millions of tons of explosive force. The largest ever tested, the Soviet Union's Tsar Bomba, produced a 50-megaton explosion. That's over 3,000 times more powerful than the bomb dropped on Hiroshima. The fireball was nearly 8 kilometers wide. The flash was visible 1,000 kilometers away. And that was with the bomb deliberately reduced to half power to avoid destroying the aircraft that dropped it. But the true horror of nuclear weapons isn't just the blast. It's what comes after. Temperatures at ground zero can exceed 1 million degrees Celsius, hot enough to vaporize steel, concrete, and human bodies in milliseconds. The pressure wave flattens buildings for miles. Windows are shattered up to 100 kilometers away. Fires break out across entire cities, combining into massive firestorms that consume all oxygen and melt asphalt. Then comes the radiation. First, the initial burst of gamma rays and neutrons that kill instantly. Then the fallout, radioactive dust and debris that spreads for hundreds of kilometers. Fallout contaminates soil, water, and air. It seeps into food. It lingers for decades. Survivors may face burns, radiation sickness, cancer, infertility, and genetic damage. Children born years later may suffer deformities. And it doesn't stop at the borders of a city or a country. A large-scale nuclear war would inject millions of tons of soot into the atmosphere, blocking sunlight for months. This phenomenon, nuclear winter, could cause global temperatures to drop by several degrees. Crops would fail, famine would spread, civilization itself could collapse. So how many of these weapons exist today? Over 13,000. The United States and Russia hold about 90% of them. Many are on high alert, ready to launch in minutes. Submarines roam the oceans with dozens of warheads. Bombers sit on runways, fueled and armed. Silos in remote regions of the world stand ready to unleash apocalyptic fire at the push of a button. Why do we still have them? The answer is deterrence. The idea is simple and horrifying. If two countries have nuclear weapons and both know a nuclear war would destroy them, then neither side will start one. This is called mutually assured destruction, MAD. It's a strategy that depends not on trust, but on fear. And yet history is filled with close calls. In 1983, Soviet radar falsely detected incoming American missiles. A single officer, Stanislav Petrov, chose not to report it as a real attack. He broke protocol and possibly saved the world. In 1995, Russia mistook a Norwegian research rocket for a potential nuclear strike. The Russian president activated his nuclear briefcase, but no missiles were launched. We have come terrifyingly close to the edge, not once but many times. And every year the risk increases. More nations seek nuclear weapons. Old systems age. New technologies like cyber warfare introduce unpredictable threats. The more complex the network, the more likely it is to fail. Nuclear weapons are not just historical artifacts of the Cold War. They are active modern instruments of power, ready to be used. And in the next part, we'll go deeper into how these weapons are built, the science that makes them possible, and the terrifying chain of events they can set in motion in less than 30 seconds. The making of a nuclear weapon is not just a feat of engineering. It's an exercise in control over the fundamental forces of the universe. Building one requires the rarest materials on Earth, precision technology, and a terrifying understanding of how atoms behave when pushed to their limits. It starts with uranium or plutonium, but even before that, it starts with mining and refinement. Naturally occurring uranium contains less than 1% of the fissile isotope uranium-235. To be used in a bomb, that percentage must be increased dramatically, a process called enrichment. This is done using gas centrifuges, machines that spin uranium hexafluoride gas at incredibly high speeds to separate lighter U-235 molecules from heavier U-238. This process is slow, energy-intensive, and technically demanding, which is why nuclear proliferation is so difficult to achieve. Only a handful of nations have the resources and expertise to enrich uranium or reprocess plutonium. Plutonium, in contrast, doesn't occur naturally. It's bred in nuclear reactors when uranium-238 absorbs neutrons. After enough time, the reactor fuel is chemically processed to extract the plutonium, which is then converted into a metallic form usable in weapons. Both materials are deadly to handle. Exposure to even microscopic amounts can cause cancer or radiation sickness. That's why nuclear programs require vast infrastructure, shielding, remote handling tools, and laboratories more secure than prisons. Once enough fissile material is acquired, the next step is to shape it precisely. In a gun-type weapon, the uranium must be machined into two subcritical masses that can fit together perfectly upon detonation. In an implosion-type bomb, the plutonium core is typically shaped into a solid sphere or a hollow shell, depending on the design. Around it, high explosive lenses must be arranged symmetrically. These lenses are not simple charges. They are designed with extraordinary care to create shock waves that converge at exactly the same time from every angle. Any asymmetry, even by microseconds, will cause a fizzle, a failed detonation. To make the implosion work, scientists use a technique called explosive lensing. By combining fast and slow explosive materials in specific geometries, the shockwave can be molded into a perfect inward sphere. This technology, along with the precision detonators required to fire all explosives at once, represents one of the most complex parts of nuclear weapon design. The synchronization must be exact. Imagine firing dozens of charges at exactly the same nanosecond. That's the level of precision we're talking about. Inside the core, to further increase yield, many modern designs include a neutron initiator, a device that injects a burst of neutrons into the core at the exact moment of peak compression. These initiators use elements like polonium and beryllium or other exotic isotopes, and they're designed to age and degrade slowly over time. Maintenance and testing of these components is highly secretive and constant, requiring national laboratories and supercomputers to simulate their behavior. But the horror doesn't stop with the physics. Nuclear bombs are made to be delivered. That means designing re-entry vehicles that can withstand the heat of atmospheric descent, targeting systems accurate within meters, and arming mechanisms that prevent accidental detonation under any circumstances. Modern warheads are stored with safety devices, encrypted firing codes, and multi-step launch protocols. But they're also designed to be launched in seconds. A single submarine can carry enough warheads to destroy hundreds of cities. A single aircraft can drop a bomb that wipes out 10 million people. Thermonuclear weapons are even more complex. A typical hydrogen bomb contains a primary and a secondary. The primary is a fission bomb. When it detonates, it compresses the secondary, usually a capsule of fusion fuel wrapped in uranium or lead, using X-rays. These X-rays cause a process known as radiation implosion. Inside the secondary, there's often a rod of plutonium called a spark plug, which undergoes its own fission and triggers the fusion of the fuel around it. The result is a staged explosion, fission followed by fusion, sometimes followed by more fission as fast neutrons slam into surrounding materials. This design is known as the Teller-Ulam configuration, and it allows bombs to be tuned to different yields. In theory, a thermonuclear weapon has no upper limit. Its yield is constrained only by the amount of fuel used. That's why the Tsar bomber at 50 megatons was only half of what it could have been. Engineers deliberately replaced its uranium tamper with lead to reduce the total energy release. A terrifying reminder that the destruction we've seen so far has been restrained. But perhaps the most dangerous part of all is the human factor. Despite layers of safety, nuclear weapons remain under the control of individuals. People who can make mistakes, lose judgment, act irrationally, or be misinformed. During the Cold War, numerous false alarms brought us within minutes of all-out nuclear war. In 1961, a B-52 bomber carrying 2 hydrogen bombs broke apart mid-air over North Carolina. One bomb's parachute deployed, the other fell into a field. One safety switch prevented it from detonating on impact. The others had failed. In 1980, a technician at a missile silo in Arkansas dropped a socket wrench which punctured a fuel tank on a Titan II ICBM. The explosion that followed killed an airman and sent a 9-megaton warhead flying from its silo. By pure chance, it did not detonate. And then there are the close calls due to miscommunication. The Cuban Missile Crisis brought the world to the edge of nuclear war. Soviet submarine officers, cut off from contact and under American pressure, debated whether to fire a nuclear torpedo. One man, Vasily Arkhipov, refused to authorize it. He may have saved the world. Every nuclear weapon ever built is a monument to potential annihilation. They represent a line that humanity has never crossed again since 1945, but only barely. The systems we've built to control them are not perfect. The people in charge are not perfect. And the machines that support them, computers, radars, satellites, are not perfect. In the next part, we'll confront the terrifying consequences of what happens when just one nuclear weapon is actually used. Not in theory, not in a test, but in a modern city today with the global systems we now depend on. The story of how humanity created the most destructive weapons in history begins in the deserts of New Mexico. In 1945, under a veil of absolute secrecy, scientists working on the Manhattan Project gathered to test the first atomic bomb. They called it Trinity. At 5:29 a.m., a new era began. The explosion lit up the sky, turned sand into glass, and sent a mushroom cloud spiraling into the heavens. Watching from a safe distance, physicist J. Robert Oppenheimer recalled a verse from the Bhagavad Gita. "Now I am become death, the destroyer of worlds." It was not just a scientific achievement, it was a turning point for civilization. Only weeks later, the United States dropped nuclear bombs on Hiroshima and Nagasaki, killing over 200,000 people and forcing Japan's surrender in World War II. The world had witnessed, for the first and only time in war, the raw power of the atom unleashed. But the real story was just beginning. In the decades that followed, the United States and the Soviet Union raced to build bigger, more powerful, more terrifying weapons. The Cold War became a standoff not just of ideology, but of annihilation. Thousands of warheads were deployed. Submarines were equipped to launch from beneath the oceans. Bombers patrolled the skies. Satellites watched everything, and humanity lived in the shadow of instant extinction. And yet, strangely, that very threat, mutual destruction, kept the bombs from being used again. The doctrine of mutually assured destruction, MAD, dictated that if one side launched, the other would respond with full force. There would be no winners, only survivors, if any. Fear became the ultimate weapon. It worked for a while. In the years since, arms control treaties sought to limit the spread and number of these weapons. The Nuclear Non-Proliferation Treaty, NPT, Strategic Arms Reduction Treaties, START, and other agreements attempted to reduce arsenals and build trust. Thousands of warheads were dismantled. Testing was curbed. But many treaties have eroded, and tensions between nuclear-armed nations have begun to rise again. Today, 9 countries are known to possess nuclear weapons: the United States, Russia, China, France, the United Kingdom, Pakistan, India, Israel, and North Korea. Others, like Iran, are suspected of seeking them. And as more players enter the stage, the chances of miscommunication, miscalculation, or even unauthorized use grow. Modern nuclear strategy is no longer just about deterrence. It's about precision, speed, and survivability. Hypersonic missiles can travel 5 times the speed of sound, reducing reaction time to mere minutes. Artificial intelligence is being explored for launch decisions. Autonomous systems raise new questions. Who pulls the trigger? A general, a president, a machine? And then there's the human element. Political instability, rogue actors, terrorism. What happens if nuclear material falls into the wrong hands? What if a weapon is detonated not by a nation, but by a group with nothing to lose? The systems that control nuclear weapons are only as strong as the people who manage them. But it's not all doom. There is still a path away from the edge. Diplomacy, disarmament, verification, and cooperation have worked before. After the Cold War, the US and Russia dismantled thousands of warheads. South Africa voluntarily gave up its nuclear arsenal. Ukraine inherited thousands of Soviet weapons and gave them up in exchange for security guarantees. There are examples, proof that nations can step back. Public awareness also matters. When people understand the consequences, pressure grows on governments to act responsibly. Education, transparency, and activism have played major roles in halting tests, closing programs, and stopping proliferation. Even now, movements exist pushing for global disarmament, reminding the world that living under the threat of extinction is not the only option. Technology can also help. New satellite systems can detect secret tests. AI can enhance verification protocols. Robotics can help dismantle warheads safely. Science gave us these weapons. It can help us control and one day eliminate them. But none of that matters if we don't care, if we forget, if we stop paying attention. Because the most dangerous nuclear weapon is not the one in a silo or aboard a submarine. It's the one we no longer talk about. The one we pretend isn't there. The one that sits quietly, waiting, while the world scrolls past. In the end, the question isn't just how nuclear weapons work or how powerful they are. It's whether we're willing to live in a world where one mistake, one glitch, one command could end everything. Not in a month, not in a week, but in 30 seconds. And if we are, then maybe we've already lost. But if we choose to remember, if we choose to act, then perhaps the countdown can be stopped. Not by force, not by fear, but by choice.